Okay, so we call that the feasible solution space, right? And please always remember that feasible solution space contains points that are all feasible solutions. That means they meet all the constraints. It's very important. Now, we need to find the solution, which is one point, right? Because it's a point that has an x1 and x2. So that's x1 and x2. So it's a point that produces the optimum value of our objective function. In this case, it's a profit. How to do that? So we need to plot the objective function. But the objective function says max 60x1 plus 50x2. How can you plot this one? Remember that 60x2 plus 50x1, it will give us a profit. So it will give us a value. That's why we know that this will result in a certain value. So in order to represent the objective function, we simply give any value here. All right. So we say that 60x, let's plot 60x1 plus 50x2 equals a certain value. Now you can choose any value, by the way. However, just to be practical, and if you are using a complete manual calculations and a graph, it's better to choose this value to be divisible by both 50 and 60, so that you don't end up with decimals, and then you will be suffering by looking at decimals into your axis. All right, so that's why I'm going to use 300 as my variable, and I will plug this one. Now I can see the objective function. Where does it fit in my feasible solution? So what I'm saying here is this: any point on this line is a point that has an x1 and x2, and when you replace x1 and x2 here and there, I will have a profit equal to 300. Okay, so we called this line, or the line, all the points on the line result in the same profit, and that's why this line is called an isoprofit line. Okay, which means iso is for equal and profit equal profit. So any point on this line, okay, will result in the same profit of 300. But that was not enough for us, right? We could visualize now how does the objective function, where does it fit in my feasible solution, but it does not tell me yet how to find my optimal solution. So let's draw another line. Let's say for a value of 600. All right, instead of 300. So let's plot it. Here we go. We can see that. What's the observation? Now when you compare the two lines, the isoprofit line of 300 and 600, we can make two observations. The first one is that the 600, which is a higher value for the profit, is farther from the origin, right? And then you can see that the two lines are parallel. Now these two observations will be very crucial for me to find a procedure to graphical procedure to find the optimal solution. Okay, why this? Because we can now project what we have observed, that as we increase the profit, we'll be also drawing lines parallel to the first line 300. Okay, but we are increasing the profit and we are going away from the profit. From the origin, sorry. And we're going to use that property to find now our optimal solution. All right, so what to do now to find the optimal solution? This is where we stopped. So to find the optimal solution, we first plot any line. Let's say for 300 was only for convenience for us. And now what we will do, because of our previous observation that as we move in a parallel manner from any line that we draw initially, any line, okay, as you move away from the origin, you will be increasing your profit. So keep going away from the origin. However, I cannot go, let's say, up to here, right? Because I will be outside the feasible solution space. So I will move away from the origin until I touch the last point in my feasible solution space, and this will be my optimal solution. Here we go. Look at this illustration. Here we go. With the ruler, you move away from the origin, and this is the last point where I touch my feasible solution space. So it is a feasible solution, and certainly it gives me higher profit than any other point. All right. So This is my optimal solution. Now all what I have to do, I need to read its x1 and x2. So I project the line to x1 and I read it, it's 9. I project a line to x2 and I read it, and that's 4. So my optimal solution is 9 and 4. All right. Now what happens if you cannot really read exactly the value? Because in this case we were lucky that we got exactly 9 and exactly 4. What if I have, for example, 9.2 and 4.3 or 4.7? I cannot see that with the naked eye, right? Most probably you cannot see that, but that's not a big problem, because what we can do then is that we know that my optimal solution is at the intersection of two lines, the yellow and the green line, and I know their equations. So all what I have to do is I will solve a system of equations of two unknown, and that's it. I will get x1 and x2 to be 9 and 4 as we found here. All right. Now the final step is, now we found the optimal solution, so we say optimal solution is 9, 4. All right, we always give the optimal solution in a pair in this case because I have two decision variables. So this is my optimal solution. If that was the question, this will be your answer, 9, 4. Now what about the optimal profit? All what I have to do is to plug these two values, 9 and 4, in the profit function, which is 60x1 plus 50x2, and this is my x1. We can call it, if you want, x1 bar. x1 asterisk. That means this is the value of x1 that maximize my profit, and this is x2 asterisk. Okay, and I plug it there and I get 740. This is the maximum profit that I can get. Okay, if I produce 9 units of computer of type 1 and 4 units of computer type 2. And here is the summary for you guys if you want to refer to it later on. It's a good summary that summarize all the steps that we have done. All right, so what we did, we plot all the constraints in order to shrink or to reduce our search area, and then we finally identified the feasible solution space. It was that yellow polygon that we have found, and then we set the objective function to any value, but my advice for you, use a value that's divisible by both objective coefficients, and then we plot the objective function line using that initial value, and then with a ruler, so you have to have a ruler with you. All right, with a ruler, move the line in a parallel manner away from the origin, because we are maximizing it, until you touch the last point in your feasible solution space, and this point is our optimal solution. Then project the lines to read the values of x1 and x2. Otherwise, you have to solve equations of two unknown, and then you plug these values in the optimal function so that you get the optimal value. All right, so I hope that was clear for you, and I'm sure you can do it on your own.